Okay, so one of the things the only thing really that we didn't cover in AP Stats this year that we are supposed to is nonlinear regression. And um, it's a perfect time to talk about it right now because you're seeing all this data about the coronavirus. And so I'm going to take a minute to dive into this as an example. The plan for me was to we finished units 1 through 9, so the plan was just to come back and finish one day of nonlinear regression, have you practice it overnight, and then move on to review. So hopefully we get back to school together and are able to do that, but if not, this will serve as the lesson, and then I will still give you that practice problem so you've at least seen it before the exam. So the problem that we're looking at, and I had it on the Word document, but I think I've gotten rid of it. So, and this is Excel. So A and B are, A is the number of days after March the 2nd. So this is actually like March the 30th, which was yesterday. And then this is the total number of COVID-19 cases in the United States on that day. Okay, so if you look at these two columns and put them on a scatter plot, you would see obviously a positive relationship between those two things. Okay, and we could fit a line of best fit through it, least squares regression line that we've already talked about, to try to predict values maybe in the middle of here, or even a model to predict where it's going to be, let's say April the 3rd or something like that. Okay, so but one thing to look at this is column C. I have the differences. So 24 is the number of new cases, I guess you could say, from 100 to 124. It went up by 24. The next day it went up by 34. The next day it went up by 63. So you can see that these differences aren't very constant. Okay, so if they were constant, then we would think that a line or a linear model would be appropriate. Okay, and but we're not seeing that. Okay, so and that would be essentially the slope of that line if these things were the same, roughly the slope of that line. So, and you can even kind of estimate an average of these goes from 24 to 20,000. But roughly the average of those is going to be the slope of the line of best fit. So, but you can tell that doesn't do a good job. And in column 4, I guess column D, you get the quotients. So I'm taking 124 divided by 100, 158 divided by 124, because if the best model for this is actually exponential, then you will see a constant quotient. So you think of like y equals 2 to the x. You have 2, 4, 8, 16, 32, 64. If you take all of those quotients, you get 2. So it'd be a constant quotient there. So you can see that it's more consistent. We're going to look at it in a minute actually on a scatter plot and take see how we think about it. Okay, so if I go to, and this might be kind of clunky because I haven't used these apps before, but I don't think it's not going to take too long. So this is our x versus y, okay? And you can tell there's a curve there, right, from the beginning. It's obvious. So there's a line of best fit. And if you think about the residuals, you have all positive residuals until you get to like right here. And then we have a bunch of negative residuals and a bunch of positive residuals. So that is a pattern, which would tell us, and I think we can C2 is the residuals. Yeah, so there's a residual plot. Yeah, so we want to see random variation or constant random variation and constant random variation. We don't see that at all. We see variation that's just strictly going down. So we can tell that a line would not be a great model for this. Okay, so in AP Stats, there's essentially 3 models that are possible. There's the line that we've spent an entire unit on. Then we have an exponential model. Then we have a power model. So in the exponential model, essentially what we're doing is we're always doing linear regression on a data set. Okay, so and I can give an example here, but so like if you had let's say y equals 10 to the x, you have 1, 2, 3, 4, that's x. Y would be, and so forth, right? So if you look at log base 10 of x, which I know you probably hear log and just kind of shut down, but I'm gonna kind of go to that in a minute. But what log of base 10 would be, if I took log of these y values, it would essentially be saying 10 to what power gives you 10, 10 to what power gives you 100, 10 to what power gives you 1,000, 10 to what power gives you 10,000. And that list would be 1, 2, 3, 4, 5. Okay, so what we actually see is that if the relationship between x and y is actually exponential, that when we look at the relationship between x and log of y, we get a linear relationship. Okay, so we actually, if that's appropriate, we just performed linear regression on this data set. Okay, so this is the equation. I've tried to front load some. This is the graph. So this is the graph of x versus log of y. Okay, now I will say this, it looks pretty good. If you look at a residual plot, let me look at that in just a minute, but go ahead and think about it. Here at the end, there's starting to be this deviation where these values are less than the predicted line. Now that would be a good thing if that trend continues, because that means that the actual number of cases is less than what we predict, these negative residuals here. So I can see some kind of pattern here, at least here at the end, where it is a good bit above and then below. So it kind of makes me think that we're going to kind of be flattening out some. Okay, so the residual plot actually shows more of a pattern than I thought. I guess this is kind of blown up because it doesn't appear like that from the scatter plot. But I guess that's the power of a residual plot. So this is kind of telling us that there, even in the linear model of the x versus log y, there is a pattern. And what that really means is that the exponential model is too strong for what's happening. And you can see that here. It's detecting underestimation here, overestimation here, kind of a good stretch of underestimation. Oh, it might be just the way that I have my line. It's not exact either. But there's definitely something wrong there with the exponential model. Okay, so, and then here we have, well, actually, let me do couple things. So, this was your, one of your multiple choice questions, or if you did the second part of section B, or unit 2. Let's see, where am I at? Oh, it's, I don't know where it is. So here, Sketchpad. So, by the way, a background here on logarithms. You don't need to know a ton. You just need to know basically what they are. Log base 100 is understood to be log base 10. And it's just saying 10 to what power gives you 100, which is 2. Log base 1,000 is 3. Okay, so that's all a logarithm is. It's just solving for an exponent, basically. And then if you see the natural log, and instead of being base 10, that's base e. So essentially this is e to the 4.6 power is 100. So natural log of 100 is just what we have to raise, roughly this number right here, this is e. We have to raise 2.71 to the 4.6 power to get 100. Okay, so that's like a little background on logarithms. Now, if you have this equation, and let's see, one of the things you might be asked to do is to predict, just like we always did, predict a y value for an x value based on like, remember that this is an equation here between x and log of y. So essentially, it is log y equals, I'll call 0.12x plus 2.01. So I should have did the text here, but 2.01. So if you have that, then let's say we wanted to figure out what our prediction would be for tomorrow. I guess it'd be to end of today. It'd be x equals 29. Okay, so it'd be the report that we get tomorrow. So x equals 29 goes into 2.01, and that gives me, yeah, I can't get the TI-84 on this Mac, so that's kind of why it's kind of clunky. Log y equals 5.49. And then, 5.49 is not what we were predicting y to be, which y is the number of cases, total cases. 5.49 is what we think log of y to be. So now the thing that you have to do is kind of undo this. And all we need is this definition. The definition of a logarithm says that 10 to the second power is 100. So in this case, it's 10 raised to the 5.49 power is y. That's our prediction. So 10 raised to the 5.49. And this is this number right here. And 309,000. And if you have been watching the numbers, you probably know that's too big. Okay? And that's what we're seeing, is that this exponential is going to overestimate that. Okay? And so we're really, what kind of graph we would be looking at is called a logistic curve. But it's not one of the three. I will mention it at the end, and I probably got 5 minutes here. But a logistic curve is probably what we're actually looking at. The last thing I want to say, I want to kind of wrap it up, is if you look at the relationship between log x and log y, so I have it down here, and you can pause it and look back at it. If that relationship is linear, then you're actually looking at some kind of power model. So like a power model would be like an x squared, or an x to the third, okay, or an x to the 2.5 power, or something like that, which is possible. Now that's not a polynomial. It's not like a bunch of powers added together. It's just a power model, which I'll show in just a second. But if you look at the last one here, this is the linear regression model for the power model. And you can tell pattern, and then we look at the residual pattern. So really none of the three that we would be responsible for in AP Stats is really going to be a good model for what's happening here with the COVID-19. It'll probably be something else. So the exponential of the three would probably be the best, but we just saw it predicted 309,000 by tomorrow. So if you look at that, look at the growth here, 143, then to 163. To think that at 29 this is going to be 309, I think that's way too high. So let's take a look at this kind of website that I have found. Where's it at? Here, which does a lot of them. Okay, and this is something called modeling, which basically are curve fitting in this case, where you're trying to find a curve that matches this data. And the power regression model, because I left a 0 in there, is not showing. But the exponential, the one thing I wanted to show is the exponential is the pink graph. So you can see this pink graph, and everybody calls this exponential growth, and it is, especially at the beginning. But very few things in the real world actually have continual exponential